The mysterious universe is a diverse place with countless stars scattered throughout its vast boundaries. Each star holds a mystery and a unique place. Every second, a new star is born and detected. Some of these stars venture alone in this vast expanse of the cosmos, while others hold their own systems, consisting of alien worlds, moons, and many more mysterious particles. Yet, as we seek to solve the mysteries of these distant worlds, we must not overlook our own solar system, the singular place where the existence of life is possible. Within our solar system lie 8 planets, numerous moons, and millions of minor celestial bodies, many still shrouded in mystery despite years of observation and research. Our journey begins with Mercury, the swift messenger of the gods, seared by the sun's fiery embrace. Next, Venus, shrouded in thick clouds of sulfuric acid, hides its secrets beneath a veil of mystery. Earth, our home, teems with life and is the only known haven in the cosmos where life has blossomed. Mars, the red planet, stirs our imagination with its dusty landscapes and whispers of ancient water. The gas giants, Jupiter and Saturn, reign as majestic titans, their immense gravity shaping the dance of moons and rings. Uranus and Neptune, the ice giants, harbor hidden wonders beneath their frozen exteriors. Beyond the planets, the Kuiper Belt and Oort cloud are realms of icy bodies, remnants of the solar system's birth. Comets, with their luminous tails, are celestial nomads, journeying from the far reaches of the solar system to grace our skies. Today, we invite you to embark on a tour of these celestial wonders, each one a testament to the beauty and mystery of our cosmic neighborhood. Let us start with the central part of the solar system, the Sun. On November 21, 2021, the Parker Solar Probe was just 500,000 kilometers away from the Sun, making it the closest any probe had ever been to our star. This meant it was the first probe to brush against the Sun's corona, the extremely hot outer layer of our parent star. But why go through numerous technical difficulties to approach the Sun so closely? What was Parker after that required it to venture near areas where everything turns to ash? To understand the purpose, we must look at what we already know about our system's star. The Sun is a main sequence star approximately 4.6 billion years old, falling into spectral class G2V, making it a typical yellow dwarf. Its surface temperature is about 5,800 Kelvin, though both colder and hotter areas exist. The star's inner layers and outer corona can reach scorching temperatures of millions of degrees, but they barely contribute to visible radiation. The Sun's average diameter is around 1.4 million kilometers, 109 times that of Earth. Its mass is 2 times 10 to the power of 30 kilograms, or 333,000 times that of Earth, accounting for 99.9% of the solar system's total mass. We're used to seeing the Sun as small, but it is actually larger and brighter than 80% of all the stars in our galaxy. Hydrogen makes up 92% of the Sun's overall volume. Hydrogen fuels thermonuclear reactions for most stars when its temperature reaches incredibly high values. As hydrogen nuclei merge, they release great amounts of energy and transform into helium, which gradually accumulates in the star's center. Currently, helium accounts for 7% of the Sun's volume and 25% of its overall mass. Besides helium, stellar matter contains other elements like carbon, oxygen, nitrogen, and iron, but their percentages are quite negligible. The Sun has an elaborate structure and consists of several layers with different properties. At the center is a massive core, which is estimated to be 25% of the Sun's overall size. The core's temperature is about 14 million Kelvin, and 1 cubic meter of its material weighs around 150 tons. It is here that thermonuclear reactions, the source of the Sun's luminosity, occur. Every second, approximately 4.26 million tons of stellar matter is transformed into luminosity. Surrounding the core is the radiation zone, which extends to 70% of the Sun's radius. The density of matter in this area is too great for it to mix thoroughly, so energy is transferred by particles of stellar plasma continuously absorbing and radiating photons. Mathematical modeling shows that the temperature in this part of the star changes dramatically, from 7 million Kelvin in its depth to 2 million Kelvin on the outer boundary. Estimates reveal that a quantum of light produced by the core may stay in the radiation zone from 10,000 to 170,000 years before moving to the next layer. The convection zone forms the Sun's outermost layer and is comparatively dense. Stellar matter here is more rarefied and changeable, giving rise to enormous vortices that carry hot plasma from deeper regions to the star's surface, while cooler plasma masses move down. These convection cells remain stable for 10 to 15 minutes before being destroyed and giving rise to new vortices. This continuous movement of matter creates a magnetic field that pervades the entire inner part of the solar system. The Sun is also surrounded by an atmosphere composed of several layers. The lowest layer is called the photosphere, which emits most of the Sun's visible light. So when we see the Sun, we are looking at the photosphere. Its thickness ranges from 100 to 400 kilometers, with temperatures fluctuating between 6,600 and 4,400 Kelvin. Above the photosphere lies a more rarefied area about 2,000 kilometers thick, known as the chromosphere. It can be observed from Earth during a total solar eclipse or with special equipment. The chromosphere is extremely hot, with temperatures fluctuating between 4,000 Kelvin and 20,000 Kelvin. Interestingly, its outer border is covered with spicules, which are continuously active jets of hot gas spurting up a staggering 5,000 to 10,000 kilometers high. The uppermost area of the Sun's atmosphere is called the corona, which consists of giant prominences, flares, and emissions that can reach up to 1 million kilometers in size. The matter making up the corona is remarkably rarefied and incredibly hot, with an average temperature of 1 to 2 million Kelvin and peaks. This is the region occasionally crossed by the Parker Solar Probe, which dives deeper into this blazing abyss with each pass. Calculations of the energy flow released by the photosphere indicate that it is insufficient to heat the chromosphere and corona to such high temperatures. This suggests that there are physical phenomena in the Sun that we have not yet discovered, which further heat these upper layers. Several scientific hypotheses attempt to explain this thermal paradox. One suggests that the chromosphere and corona gain additional energy from reversing magnetic shock waves. Another hypothesis attributes the effect to the acceleration of charged particles in the Sun's exceptionally powerful magnetic field. The Parker Solar Probe was specially designed to uncover these phenomena and study the obscure processes in the upper layers of the Sun's atmosphere. On August 12, 2018, Parker embarked on its one-way journey to the Sun. Before reaching its target, it executed several maneuvers using Venus's gravity to adjust its trajectory, drawing closer to the Sun. Equipped to withstand the Sun's searing heat, the probe features a heat shield and instruments designed for extreme conditions. Its calculated orbit brings it close to the Sun for short periods, allowing it to cool off by radiating heat into space. The probe's main tasks include defining the structure and dynamics of the Sun's magnetic fields, measuring the energy flow emitted by the star, capturing particles of the solar wind, and registering wave-like processes in the corona. As a side mission, the probe took photos of Venus as it traveled toward the Sun. To accomplish its missions, the probe is equipped with a wide range of scientific instruments, including cameras, particle detectors, magnetometers, and radio wave detectors. The mission faces several challenges, including critical temperatures and exposure to powerful ionizing radiation. Additionally, the Sun's strong interference in the microwave range complicates data transmission back to Earth. Despite these challenges, the Parker Solar Probe continues its mission. With each completed orbit, it gets closer to the Sun. In late February 2022, it passed through the Sun's corona again to collect more data. Estimates show that at its closest approach, the probe's solar shield may heat up to 1370 degrees Celsius, 3 times hotter than Mercury's sunny side and just below the melting point of iron. Even now, the probe travels at a speed of 163 kilometers per second in its perihelion, which will eventually accelerate to 200 kilometers per second, making it the fastest man-made space object to date. The probe's life expectancy is limited. As it reaches its closest point to the Sun, it will complete several orbits over roughly a year, gradually losing speed. During this time, its instruments will face extreme temperatures and powerful radiation. Eventually failing, the probe will then descend into the Sun, where it will be consumed by the plasma. However, before this happens, Parker will transmit vast amounts of valuable data back to Earth, aiding our understanding of the Sun and advancing space exploration. This will ensure that Parker's mission will not have been in vain. Now, let's fast forward to the edge of the solar system. In doing so, we will skip over 3 planets: Mercury, Earth, and Mars. Our next chapter will focus on the asteroid belt. The solar system appears to be a perfectly tuned mechanism when viewed at large. However, between the orbits of Mars and Jupiter, there's a realm of chaos. Here, hundreds of thousands of small celestial objects whiz around space in all sorts of directions. Occasionally crossing paths, they sometimes collide, producing thousands of shards and bits. This area of space is so changeable that it's nearly impossible to predict what it will look like in the distant future. Of course, we are talking about the main asteroid belt, one of the most dynamic and mysterious areas in the solar system. Today, over 300,000 small celestial bodies found here have been given names and numerical designations, and their overall number may well exceed 1 million. The study of the asteroid belt began in 1801, when astronomers spotted a mysterious object in the sky during their search for the 5th planet. This object, named Ceres, appeared to be a planet, but was so small that even the most advanced telescopes of the time couldn't distinguish its disk, making it look like a bright dot, similar to a star. This discovery led to the identification of similar celestial objects, which were termed asteroids, meaning star-like. Apart from asteroids, this region contains great amounts of cosmic dust. As it spirals up, these tiny particles scatter sun rays and create a very faint white glow known as zodiacal light. Interestingly, this glow can be seen with the naked eye in equatorial areas of Earth. For a long time, it was widely believed that the asteroid belt objects were debris from a destroyed planet. However, this hypothesis has fallen out of favor. Firstly, The total mass of all the objects in the main asteroid belt, 4% of the Moon's mass. Even considering that many asteroids may have left the area, the total mass of the remaining rocky debris is still too small to form an object comparable in size to a proper planet. Secondly, estimates show that large celestial objects cannot form in this area due to Jupiter's gravitational influence. Mathematical modeling has revealed that the largest formations in the asteroid belt never exceeded 1,000 kilometers in diameter. Jupiter's gravitational pull rendered their orbits highly unstable, causing potential protoplanets to collide and disintegrate into smaller bits, traces of which can still be observed today. Most objects in the main belt group together to form the so-called asteroid families, populations of asteroids with similar compositions and origins, likely formed from destructive collisions. The borders of the main asteroid belt are rather blurred, with most objects lying within 2.6 to 3.27 astronomical units from the Sun. These boundaries, predefined by Jupiter's tidal forces and referred to as Kirkwood gaps, destabilize the orbits of celestial objects that enter these zones, resulting in a lower object count within them. Kirkwood gaps are not only found at the conventional borders of the belt, but also inside it. Two of the most clearly defined gaps lie at 2.5 and 2.82 AU from the Sun. The asteroid belt is conventionally divided into two large areas, inner and outer, separated by a Kirkwood gap at 2.82 AU, which coincides with the highest orbital resonance with Jupiter. In the outer part of the main belt resides the largest object Ceres. Once considered a planet and then an asteroid, Ceres was reclassified as a dwarf planet in 2006 due to its spherical shape. It has a diameter of about 940 kilometers, accounting for around a third of the asteroid belt's total mass. The furthest point of Ceres' orbit from the Sun is 2.9 AU, while at perihelion, with a surface temperature that can reach 239 Kelvin, the inner belt contains the largest and most massive known asteroid, Vesta. Vesta's average diameter is approximately 525 kilometers. Its orbit is elongated, with its aphelion at 2.57 AU and perihelion at 2.15 AU. It takes Vesta 3.6 Earth years to complete an orbit around the Sun. Vesta is notable for being the only asteroid visible to the naked eye, thanks to its reflective surface, which reflects about 42% of the light that hits it. Vesta's surface temperature ranges from 190 to 20 degrees Celsius, but it was much warmer in the past. Dark areas on Vesta's surface, particularly in the Western Hemisphere, are likely basalt plains formed by volcanic activity or collisions with massive bodies. The most prominent feature is the giant impact crater Rhea Silvia, with a diameter of up to 500 kilometers and a depth of around 25 kilometers. The second largest mountain in the solar system, towering over 22 kilometers high, is at its center. This crater's diameter almost equals Vesta's size, suggesting a massive collision that produced many fragments now classified as Vesta's family of asteroids, numbering over 15,000 and making up around 5% of the known main belt objects. Many asteroid families formed from destructive collisions of large celestial objects, with some debris mutually attracting to form new objects, informally known as rubble piles. Silvia is one such example, and a mass of 1,019 kilograms. Its average density is only 20% higher than water, with estimates suggesting that cavities account for 25 to 60% of its volume. Silvia's orbit around the Sun takes 5 years, with its aphelion at 3.51 AU and perihelion at 3.12 AU. Silvia has two known satellites, Romulus and Remus, with diameters of 18 and 7 kilometers, respectively. Another remarkable object in the asteroid belt is Pallas, discovered in 1802. Pallas is the second largest asteroid in the belt, with an average diameter of around 512 kilometers. Its orbit is exceptionally elongated and tilted at 35 degrees to the ecliptic plane, making it difficult to investigate with probes. Pallas's orbital period is 4.6 years, with its perihelion at 2.1 AU and aphelion at 3.4 AU. Its surface is heavily cratered, more so than Ceres or Vesta, and mainly consists of silicate rocks with small amounts of iron and water. Like Vesta, this celestial body is considered one of the few remaining protoplanets, making its study crucial for understanding the formation of the solar system. Unlike Vesta, most asteroids cannot be seen with the naked eye or through amateur telescopes. One such elusive object is Interamnia, one of the most mysterious in the main asteroid belt. This irregularly shaped asteroid measures 306 by 348 by 310 kilometers. Despite its relatively large size, Interamnia remains largely understudied due to its dark surface, which absorbs about 93% of the light that hits it. Interamnia belongs to the exceptionally rare spectral class FF, a subclass of carbonaceous asteroids. Research indicates that its surface color is uniform, suggesting it hasn't experienced significant collisions for a long time. Its density is about twice that of water, and it is thought to consist of a hard, rocky core enveloped in a thick layer of ice, with a surface covered in fine dark dust. It takes Interamnia around 5 years and 4 months to complete a full orbit around the Sun, with its aphelion far from the 4 largest objects in the belt. The distance from the asteroid to the Sun ranges from 2.5 to 3.87 astronomical units, while its orbit theoretically crosses paths with large objects like Ceres and Pallas. The chances of a collision are minimal. The main belt contains millions of objects, from dwarf planets to tiny meteoroids the size of cobblestones. However, the distances between them are vast, often measuring thousands or even millions of kilometers, making the risk of a spacecraft collision almost negligible. Nonetheless, mathematical modeling shows that remarkable collisions occur roughly once every 10 million years, producing new debris. Although a manned mission to the main belt is not expected soon, some asteroids have been studied using interplanetary space probes. For example, the Dawn probe observed Ceres and Vesta from 2011 to 2016. More recently, the space probe Lucy launched from Earth. While its main target is the so-called Jupiter Trojans, Lucy will approach and photograph the main belt object Donald Johanson in 2025. Additionally, the Psyche project, scheduled for launch in July 2022, aims to study the largest known metallic asteroid in the main belt, with the probe expected to reach its destination by early 2026 and remain there for at least 21 months. Asteroids, though small, hold significant scientific and practical value. Some main belt objects are treasure troves, dating back to the early stages of the solar system's formation. Studying them will provide clearer insights into the processes of planetary and celestial body formation. In the future, asteroids could become valuable sources of materials for space exploration. Jupiter, a realm of colossal storms, deadly radiation, and captivating beauty, is a powerhouse whose immense mass influences even the Sun. It is rapidly becoming one of the most studied objects in our solar system, with 7 flybys, 2 orbiters, 1 still active, and 2 additional missions planned. There is so much to know about the 5th planet from the Sun. What causes its distinctive red coloration? What is it made of? What lies beneath its obscuring clouds? What do we know about its great red spot? Jupiter plays a vital role in protecting our solar system, and it's time to delve into its mysteries. Located on the outskirts of the asteroid belt, between the orbits of Mars and Saturn, Jupiter is 778 million km from the Sun on average, or 5.2 AU, and completes an orbit every 12 Earth years. The planet has a small axial tilt of only 3 degrees, resulting in minimal seasonal changes compared to Earth and Mars. Similar to Saturn, Jupiter's equatorial radius is greater than its polar radius. Jupiter is the largest planet in our solar system. While this might not seem significant, considering the Sun contains 99.86% of the solar system's mass, Jupiter's mass equals almost the rest. It is 2.5 times more massive than all other planets combined. This leads to an interesting phenomenon. The barycenter between Jupiter and the Sun is actually above the Sun's surface, at 1.68 solar radii from the Sun's center. Let's talk about barycenters. When thinking about an object orbiting another, we usually don't consider the gravitational influence of the smaller object on the larger one. However, this influence exists. A barycenter is the center of mass between 2 orbiting objects, or the point they both orbit. Due to Jupiter's mass and distance from the Sun, its effect is significant. As Jupiter orbits the Sun, they both perform a subtle dance around this center of mass, which is above the Sun's surface. Although Jupiter has the greatest mass of any planet, it is not the densest. It is the most massive due to its size. If Neptune were the same size, it would be the most massive. Conversely, if Jupiter were Earth-sized, Earth would be over 4 times more massive. However, Jupiter's diameter is 11 times that of Earth, and its mass is 318 times greater. Mass affects gravity, so Jupiter has enormous gravity over twice that of Earth, at 2.528 g at its surface. Jupiter's gravity influences every planet in the solar system, strong enough to tear apart asteroids and capture at least 67 moons. Some scientists believe Jupiter destroyed many celestial objects in the past and prevented other planets from forming, such as 4 Vesta. Jupiter's gravity might even perturb Mercury's orbit enough that in a few billion years, Mercury could either crash into the Sun or be ejected from the solar system. Currently, Jupiter could be considered the hero of the inner planets. Acting as a cosmic vacuum cleaner, it absorbs or alters the paths of dangerous objects, like long-period comets, protecting the inner planets from potential collisions by kicking these objects out of the solar system. Jupiter is the 5th planet from the Sun and is 5 times farther away from it than Earth. Despite this distance, it can be the 3rd brightest object in the night sky, following the Moon and Venus. To show you how bright Jupiter is, we can easily observe it with a handy cam. With a maximum apparent magnitude of 2.94, it can even cast shadows. Its prominence in the sky makes it a favorite target for amateur astronomers. As consumer telescopes have improved, it's incredible what details you can now see from your backyard. The cloud layer of Jupiter, which is only about 50 km thick, contains ammonia crystals similar to Saturn's. However, the coloration comes from compounds that heat up deep within Jupiter and then rise. These compounds, called chromophores, interact with the Sun's UV light when they reach the clouds, creating Jupiter's spectacular multicolored bands. These patterns change over time, but the latitude of the bands remains consistent enough to be given identifying designations, though their width can vary. Storms and turbulence occur where these bands meet, fueling Jupiter's famous Great Red Spot. The Great Red Spot is a massive storm that could easily fit Earth's diameter within it. Discovered in the 17th century, it might be a permanent feature, although it has decreased in size since observations began. The reddish color of the spot remains a mystery, with theories suggesting it is due to chemical compounds being broken up by the sun's UV light. This storm is higher in the atmosphere than the surrounding clouds, allowing it to interact more with sunlight and possibly explaining its strong color. Jupiter also hosts another significant storm known as Red Spot Jr., which formed from the merger of three storms. This storm has avoided the fate of a similar storm that passed through the Great Red Spot and could last for a couple of hundred years. Jupiter's composition is similar to Saturn's, with layers of gaseous, liquid, and metallic hydrogen beneath its atmosphere. The deeper you go, the greater the pressure, causing hydrogen to act as a metal. Beneath this is likely an ice or rocky core. Roughly 90% of Jupiter is thought to be hydrogen, 10% helium, with trace amounts of methane, ammonia, and other elements. Jupiter rotates faster than any other planet, completing a rotation in just 10 hours. Due to its non-solid nature, the rotation speed varies, with the poles taking 5 minutes longer than the equator. As a child, I wondered why Jupiter wasn't a star, given its massive size and flammable hydrogen. However, stars require nuclear fusion caused by extreme pressures at their core, which Jupiter lacks. Jupiter would need to be 75 times more massive to become a star, although its volume isn't far off from the smallest known red dwarf. Jupiter has rings, though not as prominent as Saturn's. It has 4 planetary rings, with the main ring being very thin but bright, while the others are wide but faint. Jupiter's magnetosphere is remarkably strong, 14 times stronger than Earth's, due to its liquid metallic hydrogen center. It is the strongest magnetosphere of any planet in the solar system, only surpassed by the Sun's sunspots. This magnetosphere channels solar wind to the planet's poles, producing magnificent aurorae and protecting its 4 largest moons from solar wind. However, Jupiter's powerful radiation band poses a threat, particularly to its closest large moon, Io, which receives lethal levels of radiation. Jupiter has 67 known natural satellites, with the 4 largest, the Galilean moons, Io, Europa, Ganymede, and Callisto being some of the biggest in the solar system. Ganymede, the largest moon, has a greater diameter than Mercury. Finally, an infrared view of Jupiter reveals its immense size and power. A dot at the bottom of the planet marks the impact of a space object, which could have been catastrophic if it had hit Earth. We can be grateful for Jupiter, not only for its beauty, but also for its role in protecting our solar system. Around 100 million years ago, an icy satellite ventured too close to Saturn. The immense tidal forces of the gas giant tore the satellite into trillions of small fragments. Gradually, these fragments dispersed, forming Saturn's primary ring, which was roughly 1,000 times more massive than today's rings. Over millions of years, some of these fragments were absorbed by Saturn, some bombarded its numerous moons, and others drifted away. This hypothesis is one of the most widely accepted explanations for the origins and evolution of Saturn's rings. Despite centuries of observation, Saturn's rings remain mysterious. The visible part of the ring spans approximately 280,000 kilometers, but thin clusters of dust and gas extend their diameter to around 16 million kilometers, making them 2,000 times lighter than the Moon. Only about 3% of the ring's volume consists of solid objects. The rest is made up of rarefied gas and cosmic dust. Saturn's rings are conventionally divided into several large rings, each composed of numerous thin circles separated by narrow gaps. These gaps are caused by the gravitational influence of Saturn and its many moons. Some gaps are several hundred kilometers wide. While Saturn's rings reflect more sunlight than the planet itself, some rings are nearly invisible. The D ring, the closest to the planet, consists of tiny ice crystals and frozen methane and merges gradually with Saturn's atmosphere. The more massive C ring, about 17,500 kilometers wide, contains space objects up to 2 meters in size, which make up only 0.33% of its mass. The brightest part, the B ring, begins about 34,000 kilometers above Saturn and spans 25,000 kilometers. Its thickness varies from 5 to 10 meters, with a vertical rim reaching up to 2.5 kilometers. The outermost visible ring begins 64,000 kilometers above Saturn and is 14,600 kilometers wide, containing ice bits over 10 meters and several moons, such as Pan and Daphnis. These moons may either be remnants of the destroyed icy satellite or have formed from colliding smaller fragments. Saturn's larger moons interact significantly with the rings. When Enceladus, a 500-kilometer wide moon, found 179,000 kilometers away in the E-ring region, is particularly notable for its cryovolcanic activity. Emissions observed from Enceladus indicate a subsurface ocean with temperatures ranging from 45 degrees Celsius near the surface to 0 degrees at the bottom. Due to high levels of dissolved salts and ammonia, the ocean remains liquid under a 2-kilometer thick icy crust. The surface temperature of Enceladus is around 75 Kelvin. Its atmosphere, mostly composed of water vapor, also contains nitrogen, carbon dioxide, and methane. Geysers erupt through cracks in the icy crust, replenishing the atmosphere. But when Enceladus's weak gravity allows some atmospheric particles to escape, sustaining the E-ring, simultaneously, Enceladus captures material from its surroundings, maintaining its unique chemical balance. The geyser activity on Enceladus is influenced by its orbit, with Saturn's tidal forces deforming the moon's icy crust, causing it to crack and erupt. Cryovolcanic emissions from Enceladus contain complex organic molecules, suggesting that the subsurface ocean could potentially harbor conditions favorable for the emergence of life. Approximately 300,000 kilometers away from Saturn lies its fifth largest and most massive moon, Tethys. Uniquely, Tethys shares its orbit with two other celestial bodies, Telesto and Calypso, located at the stable Lagrange points. Telesto leads Tethys by 60 degrees in its orbit, while Calypso trails by 60 degrees. Unlike the massive spherical Tethys, Telesto and Calypso are irregularly shaped and smaller, measuring roughly 20 to 30 kilometers in diameter, with a combined mass of several trillion tons. Modeling suggests that Telesto and Calypso did not form in the same orbit as Tethys, but joined it later. Tethys itself is about 1,060 kilometers in diameter and primarily composed of water ice with some rocky impurities. Its most notable feature is the Odysseus impact crater, which spans 450 kilometers in diameter and reaches depths of up to 3 kilometers. Additionally, Tethys has an enormous chasm called the Ithaca Chasma, approximately 2,000 kilometers long, 100 kilometers wide, and 3 to 5 kilometers deep. One theory suggests that the chasm formed when a subsurface ocean on Tethys froze, causing the water to expand and break through the surface. Another theory links the chasm to the Odysseus crater, positing that impact waves traveled across Tethys, creating a powerful resonance that cracked the crust. Farther from Saturn lies its largest moon, Titan, with a diameter of 5,152 kilometers, making it the second largest moon in the solar system after Ganymede. Titan is notable for being 63.6% larger than Mercury and for having a dense atmosphere and surface liquids. Titan's surface temperature is around 94 Kelvin, yet it maintains an atmosphere 1.5 times denser than Earth's. This atmosphere is composed of over 98% nitrogen, with methane and other gases making up the rest. Solar wind transforms nitrogen and hydrocarbons in the upper atmosphere into complex organic compounds that slowly settle on Titan's surface, creating an impermeable hydrocarbon smog that obscures the surface in the optical range. Titan's internal structure likely includes a massive rocky core, about 3,400 kilometers in diameter, surrounded by a dense ice layer forming the bottom of a cold, salty ocean with up to 10% dissolved ammonia. This ocean is buried under a thick crust of water ice mixed with methane hydrate, which forms mountain ridges and elevations on the surface. Lowlands and chasms on Titan are filled with lakes of liquid ethane and other hydrocarbons. Although solar wind and Saturn's powerful magnetic field strip Titan of its atmosphere, internal processes replenish it, so this atmosphere loss might take billions of years. When the Sun becomes a red giant, it could vaporize Titan's hydrocarbon haze and melt its ices, potentially making the Moon more hospitable to life. But this event is far in the future. Of course, the wonders of Saturn's system do not end here. Uranus, a significant planet in our solar system, was discovered by British astronomer William Herschel. It was the first planet to be discovered using a telescope rather than the naked eye. While much attention is often given to Mars, Jupiter, and Saturn, Uranus remains less understood due to its great distance from Earth. However, this does not mean it lacks fascinating features or mysteries. On Earth, we are familiar with rain, consisting of water, and we have heard of unusual phenomena like blood-red rain or raining fish. Saturn's moon Titan experiences methane rain, and Venus has acid rain. But did you know that it rains diamonds on Uranus? Uranus has a high abundance of carbon and hydrogen. One carbon atom and 4 hydrogen atoms combine to form methane, a hydrocarbon. Under the extreme pressure and high temperatures found about 8,000 kilometers below Uranus's surface, methane transforms into diamonds. These diamonds, however, are not like the large gemstones we might imagine. Instead, they are incredibly small, nano-sized particles. So, while the idea of diamond rain on Uranus might sound enticing, the diamonds are too tiny to be seen with the naked eye. This is just one of the many extraordinary phenomena occurring on Uranus, a planet that continues to intrigue and mystify scientists. This phenomenon is also observed on the planet Neptune. Have you ever wondered why Uranus appears blue and green when observed? The answer lies in the methane gas present in its atmosphere. Uranus experiences very high pressure, which affects how light from the Sun is absorbed and scattered. Sunlight, which appears white to us, is actually made up of 7 colors. Methane gas absorbs the red part of the light spectrum and scatters the blue and green parts, giving Uranus its distinctive color. It has been almost 64 years since the launch of Earth's first artificial satellite, Sputnik 1. To date, we have only sent one spacecraft to Uranus, Voyager 2. Much of what we know about Uranus and its atmosphere comes from this mission. Scientists have found that in addition to methane, Uranus's upper atmosphere contains a high concentration of hydrogen sulfide, the chemical responsible for the smell of rotten eggs. Due to the limited missions to Uranus, there is still much to learn about this distant planet. Observing Uranus from Earth is challenging because clouds obscure our view, and there is insufficient concentration of chemicals above these clouds for detailed study. Future missions will be essential for gaining more insight into Uranus. If a human were to land on Uranus, they would likely suffocate due to the smell of hydrogen sulfide. However, the extremely low temperatures of around 200 degrees Celsius and the presence of hydrogen and helium would likely be more immediately life-threatening. On June 20, 2017, Uranus was observed to have two large moons, Oberon and Titania. Before Voyager 2's flyby, we knew of 5 moons of Uranus, but the mission revealed 10 more moons. Some scientists believe that Uranus may have up to 27 moons, although not all have been confirmed. The planet also has a system of rings, with 11 faint rings and 2 more prominent outer rings, named Alpha and Beta. The presence of moons within these rings causes a rippling effect, suggesting the existence of additional moons like Cordelia and Ophelia. Scientists have also detected strange patterns in the rings of Uranus, possibly indicating the presence of small, yet to be discovered moons with diameters less than 15 kilometers. The temperature on Uranus has been recorded at 224 degrees Celsius, making it the coldest planet in the solar system, even colder than Neptune. When Uranus was first discovered, it was mistakenly identified as a star because the telescopes of the time were not advanced enough to clearly distinguish distant objects. As technology improved, Uranus was correctly identified as a planet, revealing its unique and fascinating characteristics. We observed that its brightness was significantly low, similar to how the President obscures other stars from the sky. Initially, we perceived only one star as human, but later we recognized the presence of additional planets, leading to a re-evaluation of the system's stability. You might be familiar with the section that has a density lower than water, enabling it to float if placed on the surface. Interestingly, Uranus, after Saturn, has the second highest density in the solar system, measuring 21.27 grams per cubic centimeter, compared to water's density of 1 gram per cubic centimeter. This indicates that Uranus would not float on water. Uranus presents unique characteristics within the solar system. While Earth has an axial tilt of 23 degrees, Uranus's tilt reaches an extreme 98.10 degrees. A day on Uranus is relatively short, lasting approximately 17 hours and 14 minutes, yet its orbital period around the Sun is around 84 years. Consequently, a single season on Uranus can last about 21 years. Moreover, Uranus exhibits an unusual magnetic field. Unlike Earth's magnetic field, which aligns closely with its rotational axis, Uranus's magnetic field is tilted at an angle of 59 degrees and includes additional magnetic poles. These discrepancies result in significant variations in magnetic field intensity across different regions of Uranus. The intensity in its northern hemisphere, for instance, can vary by up to 400% compared to the southern hemisphere. Initially, scientists hypothesized that the peculiar tilt and rotation of Uranus would produce a vast and turbulent magnetosphere. However, observations have not supported this expectation. The magnetic field of Uranus remains comparable to other planets in terms of overall intensity and dynamics, posing an ongoing enigma for researchers, as they have yet to find a satisfactory explanation for these anomalies. Neptune, the dark blue planet with a diameter of 49,244 kilometers, is the outermost planet in our solar system, situated at a distance of 30 astronomical units from the Sun, our solar system's only star. Therefore, Neptune's distance is 30 times greater than the Earth-Sun distance. This vast distance means sunlight takes approximately 4 hours to reach Neptune. Neptune is the 8th planet in the solar system, located just beyond the beginning of the Kuiper belt, which extends from 30 to 50 astronomical units. It is the 4th largest planet by diameter and the most massive of the solar system's gas giants, indicating that its gravity is significantly stronger. Specifically, Neptune's gravity is 1.4 times that of Earth's. For example, if you weigh 100 kilograms on Earth, you would weigh 140 kilograms on Neptune. However, standing on Neptune is impossible because it lacks a solid surface. Instead, Neptune is composed primarily of water, methane, and ammonia, which form a deep, turbulent liquid layer. If you descended into this layer, you would continue sinking until reaching depths where intense pressure and heat could be lethal. Neptune was not discovered until the 19th century due to its faint visibility. Galileo Galilei first observed Neptune in 1612, but its dim appearance led to its misidentification. By the 1700s, astronomers had identified Uranus as the 7th planet, but anomalies in Uranus's orbit suggested the presence of another celestial body influencing its path. This led astronomers to predict the existence of Neptune. Johann Galle, using mathematical predictions from Urbain Le Verrier, successfully observed Neptune. This marked the first discovery of a planet based on mathematical predictions rather than direct observation. Physically, Neptune's diameter is almost 4 times that of Earth, measuring approximately 49,244 kilometers compared to Earth's 12,742 kilometers. Neptune is like a large water droplet in space, composed of 3 main layers. Its core is made of iron, nickel, and other heavy elements. As we move outward from the core, both pressure and temperature increase significantly. Scientists estimate that the temperature at Neptune's core reaches about 7,200 degrees Celsius. Remarkably, the core's size is comparable to Earth, and its mass is 1.2 times that of our planet, meaning Earth could fit within Neptune's core. Neptune's second layer, known as the mantle, consists primarily of a mix of water, ammonia, methane, and rock, existing in a liquid state. This mantle layer has a mass that is 10 to 15 times that of Earth. The pressure at Neptune's mantle is immense, reaching up to 1,000,000 times more than the Earth's surface pressure. Beyond the mantle is Neptune's atmosphere, the planet's outermost layer. This atmosphere is composed mainly of hydrogen, helium, and methane. The methane is responsible for Neptune's distinct blue color. Neptune's atmosphere extends approximately 1,000 kilometers above its mantle. Scientists have divided Neptune's atmosphere into 3 parts: the troposphere, stratosphere, and thermosphere. The troposphere is the lowest layer where most of Neptune's weather phenomena occur, including some of the largest and most violent storms in the solar system. The Great Dark Spot is a massive storm comparable in size to Earth's diameter, with wind speeds reaching up to 2,000 kilometers per hour, the fastest winds ever recorded in the solar system. Above the troposphere is the stratosphere, which is the warmest part of Neptune's atmosphere. The temperature here can exceed 1,538 degrees Celsius, which is the melting point of iron. Neptune's rapid rotation results in a day lasting only 16 hours. However, its significant distance from the Sun, about 30 times the distance between the Earth and the Sun, means it takes Neptune around 60,190 Earth days, or about 165 Earth years, to complete one orbit around the Sun. Neptune shares an interesting orbital relationship with the dwarf planet Pluto. Despite their paths crossing, Neptune and Pluto follow a repeating pattern that prevents collisions. During every 3 orbits of Neptune, Pluto completes only 2 orbits around the Sun. Neptune, like Earth, has an axial tilt, which means it experiences seasons. Each season on Neptune lasts about 44 Earth years due to its tilt of 28 degrees. Neptune also has a strong magnetic field, tilted at a 47-degree angle from its rotational axis. This magnetic field is not generated by the planet's core, but by the movement of conductive fluids in its mantle. Neptune's magnetic field is 27 times more powerful than Earth's. Among Neptune's 14 known moons, Triton is the largest, with a diameter of 2,710 kilometers. Triton is unique because it orbits Neptune in a retrograde direction, opposite to the planet's rotation. Scientists believe Triton was not originally a moon of Neptune, but was captured by its gravity millions or billions of years ago. Triton's surface temperature is extremely low, around 235 degrees Celsius, making it one of the coldest known objects in the solar system. Its thin atmosphere is primarily composed of nitrogen, with traces of methane and carbon monoxide. Triton's surface is mostly covered with ice, and its skies are often filled with icy clouds. In 1989, Voyager 2 captured high-quality images of Neptune, revealing its thin rings. Neptune has at least 5 known rings, extending up to 1,000 kilometers into space. These rings are much fainter compared to those of Saturn. The majority of our knowledge about Neptune comes from Voyager 2, the only spacecraft to visit the planet. Launched in 1977, Voyager 2 provided us with invaluable data and images, greatly enhancing our understanding of Neptune and its unique characteristics. Neptune's atmosphere is composed primarily of hydrogen, helium, and methane, and its distinct blue color is due to the presence of methane. We've learned about Neptune's atmosphere largely through observations made by Voyager 2. One of the most notable features is the Great Dark Spot, a massive storm system similar to Jupiter's Great Red Spot. Its atmosphere lacks oxygen, which makes the possibility of life there very unlikely. However, Neptune has 14 known moons, some of which may harbor conditions favorable to life. Among these moons, Triton stands out as particularly promising. Triton's surface is mostly composed of ice, and it features active geysers that eject nitrogen and other particles. Recent observations by the Hubble Space Telescope suggest that there may be a subsurface ocean of liquid water on Triton, increasing the possibility of life. The tidal forces exerted by Neptune could create the necessary energy to support life, similar to the hydrothermal vents found in Earth's oceans, which sustain diverse ecosystems. Other moons of Neptune, such as Proteus and Nereid, also have intriguing features, but they have not been studied as extensively as Triton. Future missions will likely focus on exploring these moons in greater detail to understand their potential for supporting life. Pluto is approximately 40 astronomical units away from the Sun, making it a dark and indistinguishable object. At this distance, it follows an elongated orbit around the center of the solar system, completing it every 248 Earth years. Pluto's radius is 1,188 kilometers, making it smaller than all the planets and even some of their moons, including Earth's moon. Precise calculations of Pluto's mass This similarity to small celestial bodies like Eris, Ceres, and Sedna led to Pluto being classified as a dwarf planet in 2006. Pluto's long and elongated orbit gives it a lengthy orbital cycle. It first reached perihelion, the closest point to the Sun, in 1989, since its discovery, approaching within 29.7 astronomical units. Since then, the distance has been increasing and will reach its maximum of 49.3 astronomical units by 2113, when Pluto will be at its aphelion. Pluto is a distant and dim object, not visible to the naked eye from Earth. Even images from the Hubble Space Telescope show it as a murky brown disk with no surface details. To study Pluto more closely, the New Horizons unmanned spacecraft was sent in 2006, taking 9.5 years to reach its destination. During its journey, New Horizons sent back detailed images of Jupiter. In 2015, it finally reached Pluto, making about 400 observations and collecting over 6 gigabytes of data, which took more than a year to transmit to Earth. However, New Horizons did not enter orbit around Pluto, but flew past it to explore other space objects, limiting its ability to photograph the entire surface. According to current models, Pluto has a massive core, about 1,700 kilometers in diameter, composed of various forms of water ice and rocks. This core is surrounded by a 300-kilometer ice mantle, where tectonic processes might be occurring. The mantle is covered by a crust made of crystallized gases like nitrogen, methane, and carbon monoxide. Some theories suggest that Pluto's core may generate enough heat to melt part of the icy mantle, potentially hiding a very salty and toxic ocean with large amounts of dissolved ammonia beneath the surface. Pluto's surface temperature is extremely low, not exceeding 60 Kelvin. A prominent feature of Pluto's surface is Tombaugh Regio, located in the equatorial zone and shaped like a heart, hence its nickname. This region covers about a quarter of Pluto's surface, spanning 2,300 kilometers. Within Tombaugh Regio, the western part, known as Sputnik Planitia, is a smooth, light-colored plain with a diameter of 1,492 kilometers, revealed by elevation maps to be a vast lowland area. Pluto is covered with a thick layer of nitrogen ice, along with carbon monoxide and solid methane. These substances have a light coloring, causing some parts of the surface to reflect up to 90% of the sunlight that falls on them. The region is notably free of craters, indicating it is geologically young. The main hypothesis is that Sputnik Planitia formed about 100 million years ago, when Pluto collided with a large celestial body, creating a massive impact crater that filled with material from Pluto's hypothetical subsurface ocean, which then quickly froze. Certain features of Sputnik Planitia's landscape support this hypothesis. For instance, the region has numerous smooth areas ranging from 20 to 30 kilometers across, bordered by hills and depressions. This structure resembles convection cells that form in any fluid heated from below, indirectly supporting the idea of Pluto's warm interior. Surrounding Tombaugh Regio are comparatively high mountain ridges, like Hillary Montes, to the west of Sputnik Planitia, reaching 3.5 kilometers high, and Tenzing Montes in the southern part of the heart-shaped region, some peaks rising over 6 kilometers. These mountains are likely composed mainly of water ice, which is as solid as rock at Pluto's temperatures. Moving further south, there is a deep basin surrounded by massive, multi-layered ridges of ice and rock, possibly the vent of an ancient cryovolcano. The surrounding rock may be from numerous frozen eruptions, and studying their chemical composition could provide insights into Pluto's internal makeup. The eastern part of Tombaugh Regio is darker and more cratered, indicating it is much older than Sputnik Planitia. Further east along the equator, there is a chain of dark spots called maculae. These maculae form a giant structure known as the brass knuckles, stretching along Pluto's equator. They are separated by high mountain ranges and deep crevices, with Suhu Macula being the largest dark spot, measuring nearly 3,000 kilometers. Suhu Macula reflects less than 30% of the light, in stark contrast to the bright Sputnik Planitia. Its surface is heterogeneous, with undulating terrain in the west, a smooth central plain, and mountains and craters in the east. Leaving Suhu Macula, we head north to Lowell Regio, a vast valley surrounding Pluto's north pole. This area is currently the most illuminated part of Pluto's surface due to its axial tilt, which positions the North Pole toward the Sun. This illumination has likely caused the density of Pluto's atmosphere to triple over the past 30 years, despite its increasing distance from the Sun, as nitrogen ice at the pole evaporates into the atmosphere. Pluto's orbital motion is influenced by its large satellite, Charon. Both bodies are tidally locked, always showing the same face to each other and orbiting a common center of mass. Charon's surface is noticeably darker than Pluto's, with abundant water ice mixed with methane and nitrogen in some regions. In addition to Charon, Pluto has several smaller satellites, Nix and Hydra, discovered in 2005, and Kerberos and Styx, discovered later. These smaller moons are irregularly shaped, measure several tens of kilometers in diameter, and consist mainly of water ice, likely captured from the Kuiper belt by Pluto's gravity. Despite New Horizons not capturing all of Charon's surface, it revealed many intriguing features. South of the equator lies Vulcan Planum, a vast region at least 400,000 square kilometers, comparable to the size of an average European country. Here stands Kubrick Mons, Charon's highest summit, with a diameter of around 40 kilometers and an estimated height of 4,000 meters. Surrounded by a 2-kilometer deep moat, Kubrick Mons may be a cryovolcano, and the area around it may have subsided due to the emptying of an underground reservoir. To the north of Vulcan Planum stretches Ozterra, marked with many craters and separated by a system of giant ledges and crevices from Vulcan Planum. The largest of these is Serenity Chasma, 200 kilometers long, 40 to 50 kilometers wide, and up to 7 kilometers deep, challenging to explore due to the thick shadows cast by its step slopes. Further north, near the pole, lies the giant Mordor Macula, with a diameter of 475 kilometers. Its origin is still debated. The prevailing hypothesis suggests that nitrogen and methane from Pluto's atmosphere were trapped by Charon's gravity and settled at its poles. Exposure to ultraviolet radiation transformed them into tholins, which gradually accumulated in the ice. This theory awaits confirmation, which future missions may provide. Charon remains largely a mystery, as research on it is only just beginning. The Pluto-Charon system is one of the most intriguing structures in the solar system, yet it is still understudied. Unfortunately, the New Horizons probe has long since departed from the vicinity, and the celestial bodies are rapidly moving away, taking their secrets with them. Currently, the probe is more than 50 astronomical units from Earth, occasionally sending back valuable data. By around 2030, all its systems will likely fail, leaving the probe alone in the vast cold reaches of space. And now with this, we are ending this video. We hope you enjoyed this video and discovered something new today. If you did, please give us a thumbs up and subscribe to our channel for more amazing content. Thank you for watching, and see you next time.